Thank you for putting through this whole day and making it to this point. Nikitas Paslis from Pompeu Fabra about SNARK Flipper, flip and prove multiple instances efficiently.
Yes, thank you very much for the introduction. Thank you all for being here, staying up late. It was a very tiring day, I assume. Thank you for all the very informative presentations that preceded mine. This is a joint work with Angarin Tulescu and Carla Rafols about SNARK Flipper, flip and prove multiple instances efficiently. In brief, flip uses folding via inner pairing products in order to come up with a final statement to prove. Okay, so as it is usual in this kind of talks, we will start with what is a SNARK, what do the initials mean. So of course we have succeedness, meaning that the proof size is independent of the NB witness. We have non-interactivity. There is no exchange between the prover and the verifier besides a final message from the prover, the proof. Argument, meaning that soundness holds only against computationally bounded provers. Knowledge soundness, where we have that a witness is extracted, can be extracted from a satisfying proof efficiently. And zero knowledge, which means that the proof doesn't leak any information about the witness, the usual things. So let's see at a motivating application that we draw our inspiration from. And we will see at the Filecoin blockchain, which is a proof of storage blockchain. Here, the role of the provers are being played by the storage providers, and they're responsible for onboarding storage capacity, and they bound some part of their memory to store data, and they produce proof about the consistency of this data. And the role of the verifier is being played by the nodes in the network. Okay, so they are responsible for verifying the proofs produced by the provers. So in Filecoin, originally we had that each unit of storage is represented by 32 gigabytes of data. And to make things efficient, these 32 gigabytes of data is being proven by 10 SNARKs. And importantly, all these SNARKs are about the same language, and the protocol that is used is Groth16. Okay. How it works? Groth16, as usual, we have a bilinear group and the pairing. And we have a specialized SRS. The proof consists of three group elements. And the verification of the SNARK includes verifying some pairing equations. Okay, so in our setting, in the Filecoin setting, we need to verify many such proofs. So the question is how we can do it efficiently. Okay, what ways we can come up with. Originally, to verify many such SNARKs, what we would do is that we would do batch verification, which doesn't affect proof size. It reduces verification time and doesn't affect the prover time. Then we had the aggregation, which was introduced for Groth16 from SNARKpack. This is what is currently used in Filecoin, which reduces the proof size, reduces a lot the verification time, but increases the prover time. Okay. And our contribution would be this third option of how you could verify many SNARKs efficiently, which is how we can fold instance and witnesses and prove them in one shot. And the advantage is that this would reduce the total prover time. Okay. Let's go to a quick overview of how SNARKpack works, because we're also going to use some tools that are used also there. In SNARKpack, they are using, they want to prove a random linear combination of the pairing equations. Okay, and the tools that they're going to use, they are generalized inner pairing products. And they're protocols that allow the prover to prove many such equations simultaneously. They use two specific instantiations of the generalized inner pairing products, the ones that we see here. And briefly how it works is that we start from vectors of some length n, and at each step, these vectors are committed into group 1 and in group 2. They are split into left and right part, and some cross terms are sent from the prover. Then a challenge is followed by the verifier, and then they jointly come up with a new statement that involves vectors of half the length. Okay. So if we reduce at each step the length by half, then in logarithmic amount of rounds, we come up with a statement about vectors of length 1, and then the prover can just open this, send this in the clear, and the verifier can verify their correctness and the correctness of the whole protocol. Importantly, the commitment key is also halved in each round. And for the verifier, in order to verify that the final elements that are sent by the prover, that they are correct, he needs to have the final verification key. And if we use a transparent key, then this unavoidably leads to a linear verifier in the number of statements that are aggregated in the length of the original vectors. But if we use a structured key and a common trick, we can come up with a logarithmic verifier. Okay. So what are the scenarios in which SNARKPack makes sense? So as we see, SNARKPack is used to aggregate many Groth16 proofs. Okay. So in a scenario where we have many independent provers, and they all calculate their own proofs, they can offload these proofs to an untrusted third party, which can run the SNARKPack aggregation scheme in order to aggregate them and come up with a single proof. But this doesn't leverage the fact that sometimes the person that wants to aggregate is one prover that wants to create many proofs. And in this scenario, we have that the prover also knows the witnesses to the NP relations. So we hope that we can do something better. And this is where our work is based. This is the scenario. So what is Flip? First of all, let's take a look at the rank 1 CS extensions introduced in the Nova paper. We have the relaxed version of the rank 1 CS, where we also have some error terms, this U and this E. And if you have U equal to 1 and E the 0 vector, then you recover the usual language for rank 1 CS. The next extension is the committed version of relaxed rank 1 CS, where we have that both the witness and the error vector, the E, is being committed. Nova style folding from the paper works like this. The prover sends some cross terms, a commitment to the cross terms. The verifier responds with some randomness, and then they come up with a new instance, and which is a linear combination of the previous, and a new commitment to the witness, which is a linear combination of the previous. Okay. So how can one use Nova style folding in order to aggregate proofs, in order to aggregate witness and instances? Let's say that we have this specific example. We start with 4 instances and witness and error terms. So at each step, we combine 2 of them. We send the cross terms, and we update the commitments and the error terms and X and U. Okay. So in the end, we end up with a single committed relaxed R1 CS instance. Now, in this scheme, in order for the verifier to validate that the final commit relaxed R1 CS is correct, he inevitably runs in time linear to the statements that he's aggregating, because he has to verify the whole tree. So how can we do better than this, and how can we use inner pairing products? The idea is that we never let the verifier at each step see all the commitments. Okay. What we do is that we send the verifier a target group commitment to all the commitments in the first group. Okay. Of course, in the base level, in order to have started with plain R1 CS, we must have that the commitment to the E vectors is equal to the 0 commitment. So the verifier sees the first commitment to the target group, sends the randomness, gets first the cross terms, sends the randomness, and then he updates the new target group commitment. And this is done one more time, And now we are left, in the end, with a target group commitment that is a commitment to a single element in the first group, a single commitment. OK. The verifier sees logarithmic number of things. The communication is logarithmic. So we have avoided linearity. And now, in the end, the verifier needs to open this commitment to the target group in order to recover the original committed relaxed R1CS instance. Okay. So he wants to use the final key and open it. But again, the problem is that if we have a transparent key, this operation will be linear for the verifier. So again, we use the same trick, and we offload this computation to the prover. The prover proves to the verifier succinctly that the final key that he presents to him is correct. Okay. So if we have the correctness of the previous protocol of flip, okay, and we have that the final instance is indeed the committed relaxed R1CS instance, then these two together give that the original, the leaves of the tree are rank 1 CS instances. So we are left with the task to check a final committed relaxed R1CS instance after using the flip protocol. How can we do it? If we use a generic SNARK to construct a proof, a SNARK for rank 1 CS, to construct a proof for committed relaxed R1CS, then we have a linear overhead for the prover because he has to include in his proof a proof of knowledge of openings to these commitments. And these openings are linear in the original computation being done. So we borrow an idea from Nova, and we want to use a tailored SNARK for proving committed relaxed R1CS instances. And of course, we could use their variants of Spartan, and which is a universal SNARK, and prove it this way. But we observe that this is not necessary, and we can do actually something better. And because in our scenario, we just have, there is no cycles, there is nothing, so we have the same curves all the time. So what we come up with is that we can actually extend gross 16 to a committed relaxed version, which actually is tailored to proving committed relaxed R1CS instances. The way to come up with this committed relaxed gross 16 is that first we have to modify the SRS in order to support commit and prove relations. Or if somebody doesn't want to use this modification in the SRS, he wants to use something that is already there, they can use generic commit and prove techniques or sparse matrix lint check techniques to do that, to provide the link between the commitments and what the prover is proving in the SNARK. Also, of course, we have to change the equations in gross 16 because now the equation is different that the prover is proving, but this is nothing much. Okay, so the SRS change, this is the one for the committed relaxed gross 16, and I have highlighted here what are the changes that need to be done in the SRS. And also, this is the equation that we come up with. And again, I highlight this, the changes from the original version of gross 16. So to summarize, we examine the problem of proof aggregation when a single prover is producing multiple proofs and wants to aggregate them. And our contributions are the following. We design Flip, a protocol that uses inner pairing products to fold with logarithmic communication committed relaxed R1CS instances. And we construct a committed relaxed gross 16, a modification of gross 16 for proving committed relaxed R1CS instances. And here it is important that the change in efficiency from the original gross 16 is one more pairing that needs to be verified. And in the Flip protocol, the verifier needs to perform 2 pairings in order to verify the final commitment key. So conclusion, Flip and prove aggregation offers a massive reduction in prover time compared to SNARKPack. The proofs don't need to be constructed a priori. The prover has the instances and witnesses and just folds them. there is no need for expensive arithmetization of verifier circuit inside the prover in order to perform aggregation. And because we are not using, we are remaining in the same curves, there is no need for cycles or half cycles or whatever. And also, we have committed relaxed gross 16, which can be potentially used as an alternative for proving the last step of NOVA. Of course, here, because NOVA uses a cycle of curves before the final statement, and we don't have one for pairings, we can either use a half cycle and end up with, in the final curve be the one with the pairing in order to do the gross 16, the committed relaxed gross 16. Or what we could use is, like this is a very recent work from the past week, where we have this inverse lollipop construction, where we have a cycle of ordinary curves. And then in the last step, we move from one of the curves to one that supports pairings in order to perform the committed relaxed gross 16. And thank you very much to Ogo Gijevic for the construction. And this is all. Thank you very much.
Any questions? Come on, last question of the day. Who wants to do it? Someone must have a question. Okay. Well, thank you very much. So that means we're done with day one. Great job, everyone. I promise so tomorrow is going to be a little bit chiller in the room. I know it's been a little bit hot these past couple of hours. We'll make sure to talk to the hotel. And